For this example, we want to find the Maclaurin series for f of x equals cosine of x. So we want to find a power series that will match that curve. And we notice that since it's Maclaurin series, that means that its center will be at x equals 0, which is easier. Maclaurin series are easier to work with than regular Taylor series. And then we want to find the values of x for this, which the series converges, of course. We want to find the interval of convergence. Okay, so let's start with, well, we know that f of x is cosine of x, and f of 0, which is the cosine of 0, is 1. No problem. So then, remember what we want to do. We want to build the Taylor series by, of course, finding a list of the derivatives. So we need those derivatives. It's not building off of one that we already know like we were on the last example. So we need to find the kth derivatives and divide by k factorial. So I'm going to have to find all the kth derivatives first. So let's do that. So I need the first derivative at x, which would be the derivative of cosine, which is negative sine of x. And that first derivative at 0 is 0. And then I want the second derivative, which is negative cosine of x. So the second derivative at 0 is negative 1. And then the third derivative, of course, would be sine, which means it's going to be 0 again, right? Because the sine of 0 is 0. And then the fourth derivative would be back to cosine again, and we would just continue this cycle. We would just keep going like this forevermore. So it's going to go 1, 0, negative 1, 0, 1. Now think about what that means. That means that all the odd derivatives, so for example, the fifth one would be negative sine again. And that means that all the odd derivatives will be 0, and there won't be any terms for that. Interesting. So let's write it out. So if I think about writing my cosine of x is equal to, from k equals 0 to infinity, of the kth derivative at 0 over k factorial times x to the k, right? That's the power series general formula for a Taylor series, or actually this is a Maclaurin series because it's at 0 and it's just x. Okay, so for the first piece, that would be at k equals 0. So that would be 0 factorial in the denominator, the kth derivative, the 0th derivative at 0, in other words, the function at 0, which is 1 right here, and then x to the 0 plus, and then I would want to put in, well, I'm going to skip the 1 part, right? So k equals 1 is going to disappear. That's kind of what I was noticing here. So this is k equals 0, this is k equals 1, k equals 2, k equals 3, k equals 4, k equals 5. And we can note that the odd, let me just say, the f kth at 0 is equal to 0 for odd k values. Okay, which means I can skip the next term because the 1, right, the first derivative is going to be 0, and so it's just going to disappear. It'd be 0 over 1 factorial times x to the 1, but it's all going to go away because there is, because it's 0. And then the next term would be negative 1 over 2 factorial times x squared. We can skip the third one, same reason that we skipped the first one, or the k equals 1th one, that's a word. And then, so we can skip that one, and then we're going to have plus 1 over 4 factorial x to the 4, minus 1 over 6 factorial x to the 6th, plus, and it will just continue that way, right? It's just alternating positive and negative 1 for the other values. Matter of fact, I'll make a little note of that. So the kth derivative at 0 is plus or minus 1 for even k values, and it's actually alternating plus 1, minus 1, plus 1, minus 1, etc. All right, well then let's reset the k, because obviously the 1 and the 3 and the 5 disappeared, right? The k equals 1th one was right there, and then the k equals 5 was right here, or excuse me, k equals 1 is right here, k equals 3 is right here, k equals 5 is right here, and we just kind of cut them out because they weren't needed. They were all in 0. So we're going to reset k. So we're going to make it so that this is k equals 0. We're going to skip this and make this k equals 1, and then this k equals 2, right here, that term, that term, that term, and then this will be k equals 3. We're going to reset our indices to make the series work. Okay, so let's rewrite it. It's 1, because that's x to the 0 is 1, 0 factorial is 1. So it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And we can see how this is going to continue on from here. I mean, it's going to be plus x to the 8 over 8 factorial minus x to the 10th over 10 factorial, etc. Right? So this is k equals 0, this is k equals 1, this is k equals 2, this is k equals 3, k equals 4, and k equals 5. All right, so then we need to remake a series out of that. So from k equals 0 to infinity, I need a pattern that'll get me what I want. All right, for starters, I've got an alternating positive, negative, positive, negative. And since I started a positive, it's got to be negative 1 to the k, right, to get me that positive term. And then it's going to be x to the, and I'm only doing evens, 0, 2, 4, 6, 8. And you can see there's a pattern. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. So it's x to the 2k up here. And then it's over that same number in the denominator. So it's 2k in parentheses factorial. The trick is that we don't know yet what the interval of convergence is. So that we're going to have to determine. So we can leave that blank for right now, and we'll be back for it. To find that interval of convergence, we're going to need to do the ratio test, of course. So because there's factorials involved, so we're definitely going to do the ratio test. So the limit as k goes to infinity, and we want a sub k plus 1 divided by a sub k. But realize what that means. So if I take a sub k plus 1, so that's negative 1 to the k plus 1, x to the 2, parentheses, k plus 1, right? So k turns into k plus 1, over 2 k plus 1 factorial. And that's going to be divided by negative 1 to the k, x to the 2k over 2k factorial. All right, well, this is a mess. So we need to flip this all around and start canceling things, or dividing them. So this is negative 1 to the k plus 1, x to the 2k plus 2. Let's distribute that, make it easier. And then I'm going to write this as 2k plus 2 factorial, because that's what it is. Because you distribute before you deal with the factorial. And then times 2k factorial over negative 1 to the k, x to the 2k. Now, parts of this division are really easy. I mean, it's very obvious that the negative 1 to the k plus 1 and the negative 1 to the k are not only going to cancel, but they're going to be irrelevant, right? So you're going to have a negative 1 left over here, but it doesn't matter because it's all inside an absolute value, so who cares? Nobody cares. Moreover, you're going to lose the x to the 2k plus 2 and x to the 2k. Let me do those in blue here. So x to the 2k is going to cancel with x to the 2k plus 2 and just leave you x squared, because you had 2 more up here than you had down here. So there's 2k plus 1, 2k plus 2. So there was 2 extras up here. So I leave you x squared up here. And then the hardest part to see is the factorial. So let me remind you that when you have 2k plus 2 factorial, what that is 2k plus 2 times 2k plus 1 times 2k continuing on. Matter of fact, I could say 2k factorial, right? So 2k, 2k minus 1, etc. Here, I'll just do it that way. And this one, of course, is 2k, 2k minus 1, etc. So this cancels with those and leaves you 2k plus 2 and 2k plus 1 left over down there. All right, so putting it all together, we have the limit as k goes to infinity. We have a negative 1 technically on the top, but nobody cares because it's inside an absolute value anyway. So I have negative, I have an x squared, I have a division, and then I'm going to have 2k plus 2 and a 2k plus 1 down here. X squared comes out. So this is, and of course, it's actually, it's the absolute value of negative x squared, which is just going to be x squared because the absolute value makes it positive, and x squared is already positive because it's squared. So this is x squared. I actually don't even need the absolute value anymore because x squared is always positive. And the limit as k goes to infinity of, I mean, if you want to think of it as -1 left inside there, it doesn't really make any difference. But you're left with 1 over 2k plus 2 times 2k plus 1. But that's 0. Yeah? This is 0. So if this is 0, then an x squared times that 0 will be 0. So this is 0, no matter what. And that means that our interval is -infinity to infinity because we want the ratio to be, the R value ratio, to be less than, or to be finite, or less than 1. I couldn't remember my test for a second. Less than 1. So we wanted the ratio test to be less than 1. 0 is always less than 1. So for all, so that means that the interval is -infinity to infinity. I can put it right here. Right? Because no matter what x's I have, this will be 0. It will always converge. Interesting. Now putting this together with, just thinking about it, how would sine work? Well, sine is very similar to cosine, right? It's still going to have this repeating pattern. It would just be, instead of the odd values would disappear, it'd actually be the even values that would disappear. So it's like a mirror image of this one. So let me put it in. So k equals 0 to infinity. It would be -1. Instead of to the k like it is for cosine, it'll be to the k plus 1. Actually, I take that back. It's just going to be k. It'll actually end up being k just as well because it's still going to have that alternating, and because we shift, it's a reset. So when we reset, it'll work out. So it's -1 to the k, sorry. And then it'll be x to the, this is what's different. Instead of 2k, which was even for cosine, it'll be 2k plus 1 because it'll be all the odd values that survive. The even ones will disappear. It's like the mirror image of what we're doing here. And then it'll be 2k plus 1 factorial instead of 2k factorial. So they're very similar, extremely similar. And they actually have the same interval. They're both from -infinity to infinity. And I can show you that in Desmos. I built it for cosine. So you can see the power series is this purple part. So there's cosine of x. And there's the power series. Hold on, it's going to take it a second. And I've actually stopped at 13. But of course, we're saying that if you head to infinity, the graph will continue to match and match and match. Right? You can see it's mirror imaging and writing over that cosine. So if I was able to test most to infinity, which of course I'm not, but if I was able to, that purple curve and that red curve would be completely overlapping. That's just the nature of the beast. And you can make a similar graph for sine using the formula we were just seeing.